Mr. Richmond. This is your Integrated Math 2, Unit 15.1 Lesson Summary. And Unit 15, we're going to begin to look at the real numbers as well as eventually imaginary numbers. We'll talk about that later. We're going to talk about today how to classify them, what the different number types are, and whether or not these numbers are closed in mathematics. And I'll talk a little bit about what that means. We have done that before, the closure property, but we'll take a look at it again. And then we'll look at how to take a repeating decimal, or a decimal that goes on forever as a single number or a series of numbers, and how to write that as a fraction. So let's start with this. This is probably the single most important part of this section, is this diagram here. I highly suggest that you write one of these down, study it, memorize it, make sure you really know it and know how it works. So what we have is a Venn diagram kind of consisting within this. So these are the real numbers. When you talk about real numbers, there are two types of main real numbers. The rational numbers on the left and the irrational numbers on the right. You cannot be both these. That's why they're separated right down the middle. You're either rational or irrational. So let me define that first. A rational number is any number that can be written as a fraction a over b. Okay? That now includes a lot of decimals. So a decimal like 0.5 can be written as a fraction a over b. That would be negative 1 over 2. Okay? 2/3 and 1/2 are fractions. 0.3 repeating, that's 3, 3, 3, 3. That is technically a fraction, and we're going to learn how to write that as a fraction here in example 3, just so you understand that a little better. But that's actually equivalent to 1/3. So a repeating decimal can be written as a fraction. Negative 2.4 can be written as a fraction. That'd be 4/10. So it's negative 2 and 4/10, or 2/5 is the equivalent of 4/10. So there's a lot of decimals and fractions that can be written in that form, as well as numbers like 1, 2, 3, 4. Those technically can be written as fractions as well. 4 over 2 is 2, etc. So any sort of standard number as you know it, or decimals or fractions that you can write in this form, are rational. Irrational are the ones that you cannot ever write without rounding it. An example of that would be pi. As we know, pi goes on forever, 3.14, yada, yada, yada. We can round it, but if you were to try to write pi, you would never be able to do that because it goes on forever. When it goes on forever without being in any sort of distinct pattern, it's irrational. So pi does that. The letter E does that. I don't think you have learned that yet in Math 1. I can't recall, but if you haven't, you will see it again eventually here in Math 3. But E is a number kind of like that. It's near 2.7. The other things that do that are roots. So for example, root 20 or root 5. If I do the square root of 20 on my calculator, let me just show it to you real quick, I get this. So that is a non-repeating decimal, 4.47213955. It would go on forever. It would never actually end. So any square root that you can't turn into a single number, the exemptions would be root 9, that's 3, root 4, that's 2, etc., is considered an irrational number, whether it's positive or negative. So I wrote a few examples of common irrational numbers. So if you're this, then you're none of these. If you're these, then you're not this. Now, the rational numbers are the ones that we most commonly use. Now, those can be broken down into several different classes. Okay, and the way this works is if I'm in this natural number circle, well, that circle's also in the whole number circle, which is also in the integer circle, and all of these circles are in rational numbers. So what that means is if something's a natural number, it has to be everything above it. So if I'm natural, I'm also whole, integer, rational. If I'm a whole number, well, then I'm not natural necessarily, okay? Like 0, for example, is whole, but it's not natural, so 0 is whole, integer, rational. Negative 2 is not whole, so it's just integer and rational. And if I'm 1/2, I'm not any of those, I'm just rational. And all of these are real, okay? Now if you said a number like 2, yes, 2 is listed here as a whole number, but it's also listed here as a natural. So you want to go down to the lowest level you can find it in. So it's natural, whole, integer, rational, real. Okay? So let me give you some definitions of what these are, just so we can understand it a little bit better. And I try to put it more in simpler terms for you as a student to understand than the book might. The natural numbers are the counting numbers. It'd be the numbers on your fingers if you had infinite fingers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's the numbers you would count. Okay, notice that it doesn't include 0. 0 is not a natural number. Negatives are not natural numbers, and decimals or fractions are not natural numbers. It has to be strictly a counting number. Okay? Our next class up is whole numbers. How is whole numbers different? Well, it's still all those same counting numbers, but now you can include 0. So 0 really only adds one number to this list, and that's the whole number, 0. So I tried to write what it couldn't be. If you're a whole number, you still can't be negatives or decimals or fractions. What's an integer? Well, an integer is any sort of negative counting number, or positive counting number as well, or positive and negative whole numbers, since that includes it. So -2, -3, -4, -5, going on forever. 0, 1, 2, 3, 4, 5, 6, going on forever. I still shouldn't have decimals or fractions, even if they're negative. Okay, still shouldn't have decimals or fractions. So integers have no decimals or fractions. It's the only thing it can't have, really. What are rational numbers? That's our next class up. Those are positive and negative decimals, fractions, or repeating decimals. So you don't have any of those counting numbers now. Now you're going to start to get any sort of positive or negative fraction or decimal. That's really what you're looking for it to just be rational. A negative fraction or a negative decimal. And repeating is okay. They put the line over it. Repeating, that is okay. And then lastly, our irrational numbers, I already talked about. That's any number that does not repeat. Sorry, I'm struggling today. It's all numbers that do not repeat, all non-repeating decimals. Let's try that. All non-repeating decimals, just like I wrote here. All right. So for your test, I don't know. I don't know what every teacher's going to do, but I do know that I'm probably going to ask you to draw one of these diagrams. For sure, guaranteed, I'm going to put that on my test. I'm telling you now. Draw me that diagram, list some examples. Because I know if you can do that, then you can answer any question regarding these. Okay? But we could also ask you this. Just identify the sets that these belong to. And I don't know if our book here will give you this or not. I haven't checked too much, but there are some symbols for these. So natural numbers sometimes get the letter N to represent them, and they do this little fancy block thing for the start of it. Whole numbers get a W. Okay? Integers, that's where it starts to get a little weird. They start to use a Z for integers, and rational numbers get a Q, and real numbers get an R, and irrational numbers a lot of times just get the abbreviation IRR. But this has been stressed less and less in math, to be honest, so just writing the whole name out is fine too. But if you want to abbreviate it, sometimes you'll see those letters. So let's identify what sets these real numbers belong to. -4, okay? As soon as you see a negative, you go integer. Okay, now, only if it's a negative counting number though. But -4 is an integer, it's a counting number, it's negative, so I see it in my list here, so it's an integer. But remember, it can also be everything else above it. So it's an integer, which also means it's rational, and all of these are going to be real to start. So it is an integer, a rational, and a real number. 0. 0 is my first whole. Okay, it's not natural, 0 is not included there, so it's whole and everything above whole. So 0 is a whole number, a integer, a rational, and a real number. So remember, you can't be multiple, you just work your way up. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, that's a counting number. Counting numbers are called natural numbers. So this is the one that's all of them. It's natural, whole, integer, rational, and real. Okay, square root of 7. Well, do I know the square root of 7? Nope, I don't. Square root of 4 is 2, square root of 9 is 3. So root 7 is a type of irrational number. Okay, I can't actually figure out what decimal that is without rounding. So it is just irrational. But it is also considered a real number. All of these so far are real numbers. So it's irrational and real. And my last one, 1.6. Now that's 1.6, but the 6 is repeating, and repeating is okay. So this is technically a rational number because of the decimal, and real. Okay? And just as a quick bonus, some ones that kids tend to miss. Let me just throw this one in. These are two like kind of trick questions almost that can pop up. A lot of teachers will throw this on there like a negative 0.7. But as soon as students see negative, they think, oh, it's integer, it has to be integer. But remember, this isn't. Integers still have to be counting numbers. So because it's a decimal, this is automatically rational. So even though it's negative, it's rational and real. The other little trick a lot of math teachers like to do is they'll throw a root up there, but they'll throw a root you know, like root 16. And they'll say, what's that? And they're hoping you're going to go, oh, quickly see it and say irrational because it's a square root. But because 16 is the same as 4, that's the one we're supposed to classify as the simplified version. And 4 is all of them: natural, whole, integer, rational, real. So I'd list all of them. Okay, so just a couple curveballs your teacher might throw at you. Now, next we're going to talk about closure. So something in math is considered closed if any sort of operation you do to it, it stays in the same set it was before. So for example, if you ask me to check if the natural numbers are closed under different operations, I could check. So if the natural numbers are closed under addition, then any natural number plus any other natural number has to stay equaling a natural number. And it works like that for all of them. Plus, minus, subtract, or add, subtract, multiply, divide. Any of those should work. So what I'm going to do is I'm going to identify whether this is closed for all of them. Addition, subtraction, multiplication, division. How do I do that? I try my best to think of an example for each of these where it will not be a natural number anymore. Okay? Will not be a natural number anymore. So adding. Okay? What you want to look for is, can I make it negative? Can I make it 0? Can I make it a decimal? Because those are the most likely ways you're going to break something out of what it currently is. So natural numbers. Well, let's see. The lowest ones I can do are 1 and 2. Well, 1 plus 2 is 3. 1 plus 2 is 3. 3 is still natural. I can't really think of any other natural numbers I could add that wouldn't stay natural. 1 plus 6 is 7. 7 plus 3 is 10. It always stays natural. So the natural numbers are considered closed under addition because I couldn't come up with an example for that. Now subtraction, I think I can. Because 1 minus 2 equals negative 1. And negative 1 is not a natural number, it's an integer. So I've changed the status of that number, I've changed the set it's in by subtracting two different natural numbers. Okay? If you tried like 3 and 2, 3 minus 2, you would have got a natural number. So you do have to try multiple times. Try to find those possibilities. So they are not closed under subtraction. So what I'm going to do instead is write the ones that's not closed. It's not closed under subtraction. Let's see if there's any others. It was closed under addition. I couldn't think of any. Again, I usually try to think of the smallest numbers. 1 times 2 is 2. 2 times 2 is 4. 3 times 3 is 9. 5 times 3 is 15. I can't think of anything. Every time I multiply these, it stays the same. So I'm pretty sure here they're closed under multiplication. And let's try division. Again, I like to look at the small numbers here. I'm going to do 1 divided by 2. 1 divided by 2 is 0.5. 3 divided by 6 is 0.5. There's a lot of ways I can divide natural numbers and get decimals or fractions. I'm going to try to identify one of those. 1 divided by 2 is a such example. So it actually doesn't work, it changes it. So they're not closed under subtraction or division. Doesn't work under those. And then ask me to provide an example. If it is not closed, well, here are my examples. 1 minus 2 equals negative 1. 1 plus 2 equals 0.5. There's 2 examples of them not being closed, but it did work under addition and multiplication. And so really we could ask you any of these. I only chose these 2 for today, but I could check you, have you do that with whole, rational, irrational as well. Okay? So integers, how do I do this with integers? Same idea. I'm going to try to come up with an example of addition, subtraction, multiplication, and division for each. And I'm going to try a few and, excuse me, and see if I can get them to not equal an integer. So what are some integers I could add? Negative 1 plus negative 3. What's negative 1 plus negative 3? Negative 4. Negative 2 plus negative 5 is negative 6. Negative 7 plus negative 3 is negative 4, or negative 10. Well, when you add negatives, it stays negative. I kind of already know that rule, so I don't think I can actually break that. I think if you add two negative numbers, it's going to stay negative. Okay? And notice for integers, I'm using the negatives. You should try to use the numbers that separate it from this. 3 is technically an integer, right? But it's not good for the testing purposes. I want to test the ones that are like distinctly integers. Okay? So far that looks closed. Can I make it change for subtraction? Well, let's see. I'll do the same example. -1 minus -3. Well, what happens there? -1 minus -3 zip zap. So it's -1 plus 3. This actually equals +2. And 2 is still technically an integer. Okay? But it is also natural. Okay? So could I get something else? Let's see. So that's still considered an integer of sorts. So we'll keep that. -2 or -4 minus 6, -10. That's still an integer technically. So you know what? I think it works no matter what, because -1 plus 3 is 2. It's still an integer technically. It's not negative, which separates it from the naturals, but it is a type of integer. 2 is a type of integer. So I would say it's closed under subtraction as well. Let's try multiplication. -1 times -2. -1 times -2 is +2. So any negative times negative is going to equal positive. Positive numbers are still integers. -5 times -6 is +30. It's the same problem. I can do negative times a negative and get a positive, but a positive is technically still an integer. So I think it's closed under that. How about division? -1 divided by or over -2 is +1/2. Well, there we go. Now we finally are breaking that rule. -1 divided by -2 equals a fraction. So this doesn't work. That would mean it's not closed under division. And that would be my example of that. Okay, so not all these different sets are closed under the same operation. Some operations work for others and not for some. So integers was a good example where, you know, even though we got some positive numbers are considered a type of integer. So it's actually closed under those operations. Okay, and be ready to do this for really any of the type: rational, whole, irrational, the ones that we haven't done. All right, and lastly, how do we write a decimal as a fraction? Well, I kind of have a shortcut for this that I do. It's based on sequence and series without having to really teach that full process, but here's ultimately it. Like when I write a fraction, if I said 0.4 and you said make 0.4 a fraction, I would put 4 over 10 because this decimal place is the tenths. I have basically 4 tenths. If you said 0.36, well that would be 36, but this is hundredths, so I could put that over 100. And then it's just a matter of simplifying that fraction down. Well, what's nice about repeating decimals, the way they work, is it's basically the same premise, but because of this repeating process, you never truly reach a solid 10. You get as close to that as possible. It's this idea of it going on forever. So instead of putting them over 10 when it's repeating, I can put it over that same number of 9s. So if it's in the 10th place that it's repeating, I'd put it over 9. If it's in the 100th place, I'd put it over 99. So for example here, it's 41 repeating. I can actually just put this as 41 over 99. 41 over 99. And then it's just a matter of seeing if anything goes into 41, 2 doesn't, 3 doesn't, 5 doesn't. So that is really it. This does not simplify. I can actually leave that as 41 over 99. It's a little bit faster way of doing that. Okay? And for something like 0.7, well, 0.7 repeating means 7, 7, 7 going on forever. It's really repeating just in the 10th place. So I can write that as 7 over 9. I put it over the number of 9s that represent the place. And so just to give you a bonus, see if I said 0.12 repeating, 0.12121212. Well, I have two numbers repeating in that place, so it's 12 that I used over that same number of 9s, that'd be 2, so over 2 9s. And this one I actually have to simplify. I can divide both these by 3, and I get 4 over 33. Just so you got to see one where there's a little bit extra work. So that's how I simplify it. And this is basically illustrating the point of why a repeating decimal is technically a rational number, because it is a fraction. It's a fraction that I can write, I just haven't written it that way yet. So hopefully this helps you. Make sure you study the diagram, make sure you can create one. I wish you the best. Good luck.